Hello, everybody. Welcome to today's crime seminar. Today we have two talks, two speakers. Our first speaker is Jorge Urbán Gutiérrez. He will be giving a talk on exploring the applicability and the optimization process of physics-informed neural networks. Jorge Urbán is graduated in physics from the University of Alicante in 2020. His academic interests have always been related to computational physics, specifically applied to the study of astrophysics system. After completing a master's degree in astrophysics, he decided to start his PhD about a year ago, where he is currently working with his advisor and other colleagues on the applications of physics-informed neural network for different physics problems. With that short introduction, the floor is yours and you can start your presentation.
Well, thank you very much for the presentation, okay? And also I want to start by thanking you the opportunity to participate here in your seminar, okay? And in this talk, I will introduce you some, but this talk is more primarily focused in our latest work, in which we focus to understand better the training process in teams, in particular as an optimization problem, because we needed what we talk with my PhD advisor and things like that, and we felt that we needed to understand better the optimization process that is behind pins, and taking advantage that there are, I don't know, 60 or 70 years of optimization theory. So we felt that perhaps we can apply these optimization concepts and optimization theory, at least to understand in a better way the optimization process towards in physics informed neural networks, and also in neural networks in general. But here we're interested more in physics, so my PhD project is about physics informed neural networks. So maybe the most suitable title of this presentation is exploring the optimization process of pins, because maybe the applicability, I don't have time to introduce some other concepts, some other previous studies that we have made, because maybe I run out of time. But nevertheless, I have some backup slides in order to if you have the time to present the other things, I will share with you previous application that we have made in my PhD project. So this work has been made in collaboration with my colleague Petros Stefano, which is also a PhD student that is working with me in PINS, and also my PhD advisor, Jose Pons, that is more related with astrophysics and numerical methods. And we are all learning together about PINS because it's a very recent topic, no? So we are all learning together about all these things. So, okay, let me check my notes here. Okay, so this is basically a table of contents of the presentation, okay? I will give you, first of all, some motivations, of our latest work, and to see my motivation of the latest work as an optimization problem in pins. Then I will talk you about pins in a nutshell. I think you are all pretty familiar with pins, but as a warm-up, I think it's good to remember the basic things. Then I will provide you some concepts on optimization, okay, that it will be useful in order to present the results that I will share with you later. And then I will give you some take-home messages and some conclusions about the work I have been done with my colleagues. Okay, so the motivation of the work that I have been doing is that, okay, pins are nowadays have positioned as a serious contenders in the domain of computational physics, okay? And with neural networks in general, machine learning, we are experiencing a boom in all these kind of things. And in particular, the physics informed neural networks are growing. There is more and more people researching this, and we wanted to assess more the efficiency of this kind of new new kind of numerical techniques about machine learning physics and for neural networks in particular. So as pins are an optimization problem, neural networks in general, we wanted to understand better the optimization problem, the process that is behind the training process in pins. So we have two main questions that we wanted to ask it before doing this work. The first one is that if we can dive into the well-established optimization theory that is very, very well established in mathematics, for example, in order to understand better the training process of pins. And the second question is, once we understand better the optimization process, if we can enhance the accuracy and the efficiency of physics and for neural networks in particular, but maybe in other applications of machine learning. Okay? So I will present you the basics concepts first. In this work, we employ the fully connected neural networks, which are the most basic, but currently the most employed architecture pins. Although maybe you hear the Kolmogorov networks, which are now bursting in also. But nowadays, for now, we have focused on this type of neural network because they are the most standard ones nowadays in the pin literature. So fully connected neurons are motivated because they are universal approximators. That is, they have the capability in theory to approximate any continuous function. And they are structured, as you know, in layers, where in each layer we perform first a linear transformation, okay? And then in this linear transformation, we apply a nonlinear function, which is the activation function, okay? So in the fully connected neural networks, the thing that is trained, the thing that is adjusted is the linear transformation by adjusting the weights and the biases of this linear transformation, okay? For example, in the Kolmogorov neural network, the thing that is trained is the non-linear transformation directly and things like that, which are also interesting to research in more future work, okay? Okay, so pins, the function, what is a pin is basically the function that we want to represent with a neural network in pins is the solution of that differential equation. So from the output of the neural network, we can take, for example, derivatives of the output with respect of the inputs, okay? And then we can compute the residuals of this differential equation. And because we wanted to achieve the solution of the differential equation, the thing that we need to minimize is the residuals of the differential equation. So the loss function, which is the function that we need to minimize in general machine learning, are the residuals of these differential equations. So the weights and biases of the neural network are adjusted in order to minimize this loss function. And additional restrictions should be imposed, in particular, for example, initial and boundary conditions. And this can be added additional terms into the loss function, or maybe they can be imposed directly by redefining the output of the neural net. For example, for deleted boundary condition, this is pretty easy. If you have the input of the output of the neural network, which I call N, then you can redefine the output. I call this redefinition U as a sum of two terms. The first term is the function that should be accomplished at the boundary, and the second term is the product of H times the output of the network, where H is a function that should be zero at the boundaries, okay? For example. But anyway, the boundary conditions and initial conditions could be also added into the loss function, which is a more general approach, okay? So, and now I will share with you, because our work is more focused on optimization techniques and optimization theory, I will introduce you some basic concepts in optimization that it will be important when I present the results later on, okay? So neural networks in general, and particular pins, are an optimization problem because we are changing the trainable variables by minimizing a function, which is the loss function. And as you may know, the people who is more familiar with optimization, we have many methods in optimization theory, but maybe the most known ones are the so-called line search methods. Okay? So in line search methods, we basically compute two things. The first thing that we compute the direction along which we are going to move, okay, in the parameter space, which I represent by the letter P, okay? And in general, in line search methods, this direction, it can be written as a product of a matrix, which I call H root K, and the gradient of the loss function, okay? And once this direction is computed, then we need also to know how much we move along this direction. And this is controlled by the alpha sub K parameter here that is known as step length in optimization theory, but I think the most common name in machine learning is learning rate, but I think it's pretty much the same. Okay? And in optimization theory, there are many algorithms in order to find the most suitable learning rate or step length from given a particular direction. But the most critical thing that defines the method that we are using, the algorithm that defines the algorithm that we are using, is the choice for this matrix, HK, which give name, as I said, for the different optimization methods. For example, gradient descent uses some expression for this matrix, or Newton or quasi-Newton methods use other expression for these matrices, okay? But in general, line search methods can be casted in these two equations that I presented here, okay? So before moving to different optimization algorithms, I want to share also with you a potential problem that can appear not only in things, but also in general in optimization, which is the problem of field condition. So the problem of field condition, I think, is pretty easy to understand. We say that a problem is field conditioning, which is essentially very badly scaled. That is, in the parameter space of the loss function, we have some directions on the trainable variables where the function changes much faster or much slower than others. So in order to have a clear geometrical intuition of this, I have plotted some 2D loss function. I plotted in particular the contours of the loss function, and the minimum is supposed to be at the center of the figure. So, for example, in the first situation I plotted here, the parameter space is more balanced in all the directions. So at the end, we have more rounded contours around the minimum. Whereas in the second situation, we have more elongated contours, because in this particular situation, I think that in the vertical direction, the loss function changes much faster than in horizontal direction. So in the second situation is where we can need condition. Okay, so we have, as I said, that the problem varies too much depending on the direction that you are moving to. So this is a potential problem, especially in gradient descent-based methods, because gradient descent, these methods advance towards what we call the steepest descent direction, which is the red arrows that you may see here that are perpendicular to the contours. So if this is very elongated, you will get an eternal zigzagging, okay, instead of going more smoothly towards the minimum, which is located here at the center of this figure. Okay? And also, more general way to see this field conditioning problem is if we look at the eigenvalues of the Hessian around the minimum, no? Because the function around the minimum can be expanded, no? Up to second order, for example, as the function on the minimum plus the quadratic form of the Hessian, which is controlled by the eigenvalues. So in particular, if you have a very large eigenvalue associated with one particular direction, the loss function will change much faster than in some other directions associated with low eigenvalues. Okay, so one potential way of looking this field conditioning thing is that you check the eigenvalue that you are obtaining when you try to approach more towards the minimum. Okay, and in particular, other potential problem that could also appear in gradient descent methods, is where this distribution is located towards very, very low eigenvalues. So in particular, you will have very low curvature along the minimum, and this will make that gradient descent methods and other types of methods by the well will struggle in order to converge and in order to advance and towards the minimum. And in pins in particular, this is a problem or could be a problem because we wanted to raise the precision of our solution. If the rate of convergence is very slow, then maybe we need tons of trainable variables, and maybe it's more a problem of optimization more than adding trainable variables. But this is something that I will talk about it later. Okay, so other types of methods in optimization are the quasi-Newton methods, which are, I think, more employed nowadays than the gradient descent-based methods, such as, for example, at least in pins. So in quasi-Newton methods, I think the most intuitive way to think quasi-Newton methods is to remember the Newton's method. In Newton's method, you basically expand the function around a given point up to second order, and then you use this approximation, this expansion in order to get the minimum, okay, of which is this minimum is what we call the Newton's direction, okay, and the Newton's direction is given by the inverse of the Hessian matrix multiplied by the gradient. So in Newton methods, the HK matrix that I said before is essentially the inverse of the Hessian matrix of the loss function. And the Newton's method, in general, is more robust than the gradient descent method, especially for conditional problems. But for high dimensional problems, it's very slow because we need to compute all the derivatives in order to compute the Hessian. But maybe more importantly, you need to invert this matrix. If you need tons of parameters, as the order of the computation for inverting a matrix is ordered in cube. This could be very, very expensive to compute. So quasi-Newton methods is a method that lies in between, so to speak. So in quasi-Newton methods, the matrix HK is some approximation of the inverse Hessian that is constantly updated in order to get more and more accurate matrix in order to get to resemble more and more the inverse Hessian matrix. Okay, and in order to update these matrices, there are many formulas in order to update them. And depending on the formula you are using, you are with different quasi-Newton methods. Okay, and in particular, a broad class of quasi-Newton algorithm can be casted of what we call the self-scale Broyden formula, which is given by this pretty large expression. But basically, what you are saying is, given the matrix HK and these definitions, you compute the matrix HK at the next iteration. Okay, and this formula is controlled by two important parameters here, which is the tau k parameter here that appears and at first, and then a phi sub k parameter. And these two are scalar values, control or say which formula we are using. For example, the BFGS formula is recovered. Well, BFGS formula is a type of quasi-Newton method, which is pretty popular in optimization, but I think also in pins. Because I have seen that it is very used in this kind of applications. Is recovered if we make the tau k parameter here equal to 1 and phi k equal to 1. And BFGS is pretty used because it's very competitive in many applications in optimization, but some computational results from 50 or 40 years ago suggest that when we have ill conditioning problems, in certain type of ill conditioning problems, it could particularly suffer because yield stagnates and the convergence rate starts to be very slow as we get more and more towards the minimum. So because of that, many variants of this formula given by changing these coefficients have been proposed in optimization literature in order to address this issue. So in order to explain the motivation of the different choices proposed for these coefficients, I will move to the next slide, and where we'll see the connection between quasi-Newton methods and gradient descent methods. So basically, it's a change of variables. In particular, you define this new space that I call set, okay, in terms of the original trainable variables, which I call theta, okay? And if you substitute these variables into the general formula of line search methods, you get the usual formula of gradient descent, okay, which is given by this expression. So the matrix H sub k, and what it does is to map the parameter space theta to another better conditional one that I call set, okay? So this depends crucially of the expression of the matrix that we are using, okay? So in order to check how good or bad condition in this new set space, we can compute the spectra of the Hessian in this set space, which is given by this expression, okay? So because we have seen the connection between the gradient descent-based method and the problems that they have a very conditional problem and quasi-Newton methods, this quantity, the spectrum of this quantity, is then a good indicator of the convergence rate of the different optimization methods, as we are going to see in the following slides, okay? So now I pass in order to expose the result that we have obtained in our latest work. And so we applied all these previous concepts of optimization that I said before in order to try to understand better the inconvergence. So as a baseline case, we begin with a problem with which we are particularly familiar with, which is modeling neutron star more magnetar, because we are neglecting rotation, magnetar magnetospheres in astrophysics, okay? So what we want to know is the magnetic field in all points of the magnetosphere of an neutron star. So in order to compute this, we need differential equations. The differential equations that we need to solve in general are the force-free equation, which is basically saying that the Lorentz force is equal to 0, because you have the current, okay, which is the curl of B times B equals to 0, because we are in a static situation. And also, you need to assess that the magnetic field is divergence. So we have to obtain, so we have to solve another differential equation, which is the divergence of B equals to 0. This is in general, okay? In particular, although we are extending this, we have solved this equation in the axis symmetric regime, which is basically saying that you have derivatives in the phi component. So in this case, you can express the magnetic field in terms of the decomposition, is the toroidal or poloidal decomposition of the magnetic field in axis symmetry in this particular case, in terms of two functions, which are P and I call it also the other one T. And is given by this decomposition that, for example, if you take the divergence of this expression, you will get that the divergence of this is 0, okay? So the only thing that you need to solve is the force-free condition. And if you substitute the composition into the force-free equation, you get that the function T is indeed a function P. So you only need to know P in order to get the magnetic field configuration in the magnetosphere. And then if you want to compute P, you need to solve a differential equation, which is given by these two lines at the end of the slide. This equation is in astrophysics is called the Graf-Safran equation, okay, which consists basically in two terms. The first term is a linear operator P, and then you have a source that is in general nonlinear, okay? That complicates the problem because it introduces non-linearity, okay? So in order to have a better intuition of the optimization process, we consider the simple case, which is T of P equals to 0, which is the linear problem. And we begin with this case because we have analytical solutions for this particular problem, so we can make more direct comparisons in order to assess the performance of the different optimization methods that we will explain in a couple of minutes. So we started, for example, in order to get familiar with the problem, we started by comparing the performance of the Adam optimizer, which is the Adam optimizer, which is a very popular optimization method in machine learning in particular, and the VGS optimizer, which I described before. Okay, so top right of this frame shows the evolution of the loss function given with Adam, which is the purple line here, and the combination of Adam for the first iterations and BFGS until the end. Okay? So BFGS achieves a much more rapid decrease than Adam, which is approximately 5 or 6 orders of magnitude approximately. And this can be explained by looking at the conditioning of the Hessian. Because if we observe the Hessian in the theta space that I defined before, which is the trainable variable space, you will get an unconditional problem because you get a very elongated eigenvalue spectra, and in particular, you also get very low eigenvalues here. So the problem is very ill-conditioned, and it has also very, very low curvature. So because of these two reasons, the Adam optimizer struggles a lot in order to converge towards the minimum solution. BFGS, on the other hand, handles this situation much better. But as I said before, BFGS, some computational resource of optimization methods suggest that BFGS is maybe not the best choice in order for this kind of situations. So in order to assess the performance of BFGS, what we wanted to check is the conditioning of the problem as we get more and more, as we get closer, more and more closer to the minimum. Okay, so in order to do that, we introduce additional iterations with a fixed training set. Okay, for simplicity, we have taken a 100 grid, for example, and we let the pin to be trained until a very low value of loss is achieved. We selected, for example, 10 to the minus 13. So in order to be as close as the minimum as we could. Okay? So once we get there, we have computed the eigenvalue distribution of BFGS in the set space. And the main conclusion here is that BFGS is not able to precondition the problem, precondition the problem in an effective way. Because if you compute the Hessian in the set space of time with BFGS, you get a very broad spectrum again. It is true that it manages to move some directions towards one, which is the thing that we want, because we wanted that the HK matrix should resemble as much as possible the inverse Hessian matrix of the loss function. But nevertheless, BFGS is not able to precondition well the parameter space, and because of that, we started to think that maybe, as previous results in optimization suggest, that BFGS for ill conditioning problems is not the best choice that we can think about in order to improve the results that we improve the results, at least for this particular problem. But as I will show you, this seems to be pretty general for many problems that we have tried. So the next thing, that we have seen is, okay, we check that the BFGS formula is not able to precondition the space very well. Okay? So as optimization papers suggest, we can try to modify the parameters tau 5 that I introduced you later, with the goal of have a better condition Hessian in the set space, and hence we accelerate the rate of convergence in, at least for this particular problem. Okay, so the thing that we wanted the situation that we wanted to correct is given in this sketch. basically, well, we have the eigenvalues of the BFGS, which are labeled with the letter lambda here. And the thing that we want is to narrow the spectrum of the eigenvalues of the quasi-Newton of the set space. Okay, and in particular, we wanted to narrow them very close to 1 because, as I said, we want that the HK matrices should resemble as much as possible the inverse Hessian matrix of the loss function. Okay, so now we check the effect of these parameters, and the particular expressions of these parameters. Well, there are some combinations of that. I will give you this. I give you these particular choices that we have tried in our work. I put here the reference, but well, we check the performance of some combinations of these parameters that they seems to have a good results in optimization theory. Okay, so here I plot the loss function versus iterations for the Adam optimizer, the BFGS optimizer, which is the first two curves that I showed before. But then we introduce these coefficients, these combinations of these coefficients, in order to see if we can improve the convergence for at least for this particular problem.
Jorge, can I ask a question?
Okay, yeah.
So these parameters are changing every iteration, right?
Yes, exactly. Yeah.
So you actually have to have a plan for it. You cannot just try manually, and so you have to have
no. These parameters are changed. It depends also on the matrix HK that you are evolving towards the optimization problem.
Right. Okay.
Okay. Okay. So these parameters, well, there are many combinations, and maybe these are not the most suitable ones, but nevertheless, when these parameters can achieve at least for this particular problem, we get very promising results because we achieve the reduction of the loss function significant. We achieve to reduce the loss function in a significant way. I think that there are more 2 or 3 orders of magnitude without sacrificing the computational time, because these parameters are pretty fast to obtain. Okay, so in order to assess the performance of these parameters, in order to understand better the effect of these parameters into the convergence rate, as before, we have introduced an additional iterations with a key fixed training set, as before, until a very low value of loss function is achieved, okay, which is the same as before, 10 to the minus 13. Okay, so here with BFGS, in order to arrive to this particular value of loss, I needed approximately 10,000 iterations in order to get there. Okay, and because of that, I obtained a very ill-conditioned spectra in the set space for BFGS. However, if we now repeat the same experiment, introducing these coefficients, some combinations with these coefficients, we get a much more better conditional space in the set space. You will see, for example, that the eigenvalues are more concentrated, no? And in particular, we have achieved what we wanted to get. That, for example, if you look at the maximum of this distribution, it seems to be pretty close to 1, which is the thing that we wanted to achieve. So because of these two reasons, the convergence rate is accelerated very substantially. And yeah, instead of needing 10,000 iterations, we only needed approximately 500, no? Which is a pretty decrease in the number of iterations needed to get to this particular value of loss. Okay? In order to, before moving to a more complex case, other thing that we have tried is to So to try to different options of the loss function, because some computational results also in optimization theory suggest that the BFGS algorithm becomes inefficient when the problem can become ill-conditioned, but also when the Hessian, or when we approach the Hessian towards the minimum, becomes singular, which is equivalent to have that in the eigenvalue distribution, you will get that the majority of the directions and the majority of the eigenvalues are concentrated towards very low values, because then if you do the determinant, you get practically a singular Hessian matrix. Okay, so, and this effect seems also to increase with the number of training values. Okay, I provide you here the references in order if you want to check this in a more detailed way. So another possibility that we have explored is to increase the curvature by rescaling the Hessian. That is, you move the distribution of the eigenvalues towards the right. Okay, and this can be achieved, for example, if we evaluate the mean square error, which is defined by the letter J here, through a non-monotonically increasing function J. Okay, and I define this new loss function J sub G. If you compute the Hessian of this new loss function, you will arrive to this expression, which is pretty easy to get. And in particular, if you are very close to the minimum, this term, the first term dominates in front of the other one, and at the end, very near to the minimum, you have that the Hessian of this new loss function is the Hessian of the older one multiplied by the derivative of G with respect to J. So if we want to increase the curvature of the trainable space, the thing that you need to have is that the derivative of G should be greater than 1 when you are at values of J which are closer to 0. So two obvious choices of this are the square root of J and the logarithm of J. There are many others, but we have tried the most obvious ones, for example. And in particular, the logarithm introduces a much more decrease in the parameter space than the square root, for example. And in order to assess the performance of these loss redefinitions, we have plotted again the loss function, the mean square error. Okay, this is the mean square error. Okay, not the loss redefined. This is the loss function, mean square error, as a function with iterations. Now we have fixed the optimization algorithm. Okay, but we have used this other. We have used the BFGS method, but we have trained against these new loss redefinitions. Okay, and we obtain that again we can accelerate the convergence rate of the convergence rate towards the minimum of the solution. In particular,
I have a question.
Okay.
So previously, the phi k's and tk and tau k are depending on the problem you're solving, the specific problem with the.
No. Tau k and phi k does not depend on. Well, we have taken always the same. The same expressions. Okay, for all the problems that we have explored. Okay, the tau k and phi k varies with the iterations, but not the specific formulas are the same. Okay, for all the problems that we have tried.
So it does not depend on the. Here the redefinition, the G of J is agnostic to the application, right?
It's agnostic to say that.
If I do Navier-Stokes, for example, it would be the same thing.
We have tried many problems. We have obtained pretty similar results. And in particular, so I don't know if it is pretty general, but at least we have tried many problems, as I will show you later, and we get the similar things.
Okay, all right, thank you.
Okay, so the thing is that if for your particular fund, for example, but I think at least I have seen that this is pretty general, that your eigenvalue spectrum is very located towards very low eigenvalues. You can suspect that this kind of redefinitions of the loss will enhance the performance because you are increasing the curvature towards the minimum, and this could accelerate the convergence of the BFGS algorithm. Okay? And as I will show you later, this is for the problems that we have tried that are very diverse. This seems to be pretty general. Okay. Okay, so I move the first and the next slide. In order to assess the performance of this thing, we have repeated the same experiment as before. In particular, we have taken the same training set. We arrive to the same values of loss, which is 10 to the minus 13. And we get this distribution of the eigenvalues in the set space. Okay. So again, we obtain a better conditional set in the Hessian space with this loss redefinition. I think this is done with the logarithm of the mean square error. But nevertheless, it's slightly worse conditional here than before. And because of that, we needed more iterations in order to get there. So before we needed only 500 iterations, and here we needed 1,000 approximately, even a bit more, but in this order of magnitude. Okay, but nevertheless, again, we have obtained a significant decrease in the loss fraction that could be explained again by looking at the conditioning of the problem in the set space. Okay, so now we move to a more complicated, so the same equation again, but we can complicate the problem in two different ways. The first one is adding multiples in the surface of the neutron star, which is equivalent to have a more oscillatory solution. And the other thing is to add a nonlinear source into the differential equations. Okay, so we introduce nonlinearity that always introduces difficulties. So we have to take care of this in this particular problem because for some choices of this T of P function, the solution does not exist. So we have explored the literature, and in particular, we have taken this expression for the T of P, which is basically saying that you introduce nonlinearity in a region, in a compact region in the magnetosphere. And also we have added more multiples. So at the end, at the right of this frame, you get some more complicated, a magnetic field which is more intricate with more magnetic field loops and something like that. So in order to achieve a comparable precision, we needed to raise a little bit the number of trainable values of the network. Okay? But well, nevertheless, I put here the results that we have obtained for this more complicated problem. So again, I plotted here the loss function, which is the mean square error of the differential equation as a function of the iterations. Now I consider more iterations in order to get there. And I tried, as before, to the same coefficients to modify the BFGS formula by introducing the same coefficients as before. Okay, and also I will fix the training algorithm. I consider BFGS in the right side, but I modify the loss function. Okay, I trained in this case again against the against the square root of the mean square error and the logarithm of the mean square error. And as before, I get similar results. In particular, for example, if you look at the difference between Adam and BFGS, and between BFGS and the some combinations of these parameters, which is the yellow line here, the performance is even better if you compare Adam and VGS, and if you compare VGS with this modification of the VGS formula. So in conclusion, the main conclusion here is that in order to improve the results, we need to pay more attention to the optimization algorithm, because it could have a great impact in at least in the convergence of pin problems. Okay. Now I analyze here the convergence, but we can also analyze the precision. Okay, so for the Grad-Safranov equation, for nonlinear pins or nonlinear PDEs, in general, we don't have an analytical solution. So in order to assess the precision in these particular situations, we have proposed another method that in order to estimate the precision that we have obtained with the pin. So the idea is, after the neural network is trained, we create a regular grid of a given resolution n0, and from the values of the pin given at the nodes of this mesh, okay, we can calculate the residuals of the finite difference version of the PDE. So basically, we are writing the PDE in the discrete version by using the discrete formulas for the derivatives. And we can write this for a given order of the derivatives, I call it D. Okay, so if they are calculated, these residuals with the exact solution, they should decrease as the order of the approximation error, no, the approximation of the discretization error, which is a power law, which is the resolution to the power of minus d, which if you represent it in a logarithmic scale, you will have a slope, a straight line with slope equals to minus d. Okay? But as the pin has an intrinsic error, this power law is satisfied only up to the point when the intrinsic error of the approximator starts to dominate. And as I will show you later, when this happens, you will get that these residuals starts to stagnate, and this stagnation occurs when at the value which is the generalization error of the pin approximation. Okay? So the value of the resolution at which this stagnation occurs can give us an estimate of the equivalent precision that we could obtain with a finite differentiation of a given order. So I think this is we can understand better this with an example. Okay, so what we have done here is to discretize the PDE using a second order difference method. Okay, so because of that, I plotted here the line which is the resolution to the power of -2, because I have taken second order different a second order different SEM. And I want okay, so for this I compute for a given resolution, for a given mesh, I compute the L2 norm of the discrete version of the PDE. And this L2 norm is the bunch of points that you will see here. Okay, so I repeat this for increasing resolutions, and for very low resolution, you will see that these residuals drop as we expected, as a power law with a slope given by the order that you have chosen in order to compute your derivatives in numerical differences. But then, as you raise the resolution, for example, the pink dots here, you will see here that the pink dots here start to stagnate. And this stagnation is due to the fact that you are using a pin, so you don't have a perfect solution. So because of that, this power law starts to stagnate to a finite value. Okay, and this stagnation occurs approximately at I think 500, for example. So for example, the solution get with the BFGS formula for this problem can be equivalent or at least comparable with a numerical solution obtained with finite difference with this resolution, okay? At least global.
Excuse me, can I ask a question?
Yes.
Hi, my name is Juan. I'm a PhD student here in Professor George School.
Okay.
For all these cases, I assume that you're fixing the number of iterations, right?
What?
For all the cases, you're changing the number of parameters, but you're fixing the number of iterations, right?
The number of trainable variables is the same for all the cases here, and also the iterations. The iterations are this number of iterations. Okay, for all these cases.
Oh, okay, but when you do that, okay, it looks like they converge, because my question was like, maybe if you use a model with more parameters, you may need more iterations to converge, because ideally you have to learn more parameters, right? So for all these cases, did you wait until your relative L2 or some way when you wait until you converge, like for all the cases?
Yeah, I consider the same network models for all these cases, and I wait until I have a flat loss function. Okay, so I will not advance more.
Oh, okay, great, thank you.
Okay, you're welcome. So, okay, as I explained, for example, the BFGS formula obtains the precision of for example, for the BFGS formula can be at least comparable to a numerical method that uses a second order difference scheme with a resolution which is approximately 500, yeah, which is where these residuals stagnate. Okay. But on the other hand, when we introduce these modifications of the algorithm, the training algorithm, for example, or when we modify the loss function, but we fix the training algorithm, we obtain also a much more accurate results, which is the thing that we expected, because the loss function has decreased by many orders of magnitude, by the way. So in particular, if you look, for example, the accuracy obtained for this problem obtained with the yellow dots here, which represent some combination of parameters, the same combination of parameters as before in the BFGS formula modified, you will get a much accurate result, because you see that these residuals indeed are still dropping for resolutions which are of the order of 2000. Okay, so the modifications that we introduce here accelerate the convergence, but also we are able to get much more accurate results than the standard way of training, which is using the BFGS formula or the low memory variant of BFGS formula together with the mean square error of the loss function. Okay, so these modifications, at least for this problem, works. Okay, but as we will show later, this seems also to be pretty general for various problems that we have tried. And okay, and related with this, we can also perform a parameter study where we see how the accuracy is improved by adding trainable variables. Okay, so I have plotted here the values of the residuals at which the stagnation occurs for the BFGS formula for 1, 2, or 3 layers as a function of the neurons, and for the BFGS modification that we have obtained, that we have introduced in this work, and also for the loss function modification that we have also introduced here. In particular, we consider the logarithm of the mean square error. So the principal conclusion that we take from here is that refining the optimization process can indeed be much more important than increases the number of trainable variables. Because, for example, with VGS, we get a decrease with the neurons, but the decrease that we have obtained with our modifications of the, for example, of the VGS formula is much more faster. So this led us to consider much neural networks with much less trainable variables in order to get a given precision, in order to get a desirable precision. So the idea is that by refining the optimization process, you can also obtain much more accurate results with networks that are very much smaller in size. Okay. Okay, so now I move to other problems because we wanted to check that this analysis is not tailored to Newton star magnetosphere, which is one of the applications that we are interested as we are in an astrophysics group. Okay, and we cover cases with varied cases, for example, with higher order derivatives or more dimensions, or various degrees of non-linearity, of time dependence also, systems of equations. And the particular problems that we have tried are these ones, which are labeled here. I put here the references in order to check the original works, okay, that they treated these kind of problems. And the detailed description of each problem is detailed in our work, okay, that I also provide here the reference. So here I plotted the loss function, for example, as a function again of the iterations. The models for all these curves for a given problem is the same. So for a given problem, we fix the number of trainable variables, and we fix also the number of iterations. Okay, so we get, for example, the loss function with Adam, which is given by the purple line here, the BFGS formula, which is given by the pink line here, and we have also introduced the modifications either in the loss function. So we have trained BFGS as a function of the logarithm, the mean square error, and we plot the mean square error here also. And we have also considered the combination, the same parameters tau k and phi k as before, as the previous problems, and we get these curves, so the yellow one. Okay? So it seems for a bunch of problems that we have tried that these modifications are pretty general indeed, and this is attributed, as I said, as a bad conditioning of the Hessian in the set space obtained with BFGS. And with this modification, you can enhance the results by increasing the rate of convergence of the different problems that we have tried at least. And finally, we have made a comparison with the literature. So in the literature, they use, for example, the BFGS formula, or particularly low memory variant of the BFGS formula, which is the LBFGS. And the LBFGS, as the BFGS algorithm, suffers also when in conditional problems. This is a very well-known concept in optimization theory. Indeed, this is a matter of research because they wanted to have an algorithm that is more efficient, because the low memory variant is faster than the BFGS, but to also fix the problem of the condition. It's a matter of research in optimization. But nevertheless, when we tried, for example, the BFGS formula, yeah, it's faster per iteration for a given network, but as the BFGS algorithm is more efficient for this type of situations, if you reduce the number of trainable variables, you indeed have, in comparable training times, you may have comparable or even better precisions with BFGS than with the low memory variant of BFGS in same computational times, because with BFGS you have reduced the number of trainable variables needed in order to have the desirable precision. But nevertheless, as we have seen, the VFGS is not the best, or it doesn't seem to be the best algorithm for the particular problems that we have tried. And with our modifications, either into the loss function or either in the optimization process, we can achieve in comparable training times much more better accurate results. Okay. So as I said, the optimization problem is a very important thing that we need to take care in, at least in PINs, but also I think in general current machine learning applications. Okay? So the take-home messages are that by applying well-known concepts of optimization theory, we have enhanced the convergence substantially for many problems that we have tried. The optimization algorithm and the choice of loss function can play a pivotal role in PIN convergence. And also the ideas presented in the world of physics in neural networks, which are a lot because we have many papers, and maybe can be combined with the optimization techniques that I exposed here in order to raise the performance of PINs for the particular problem that we are exploring. So yeah, these are the references. That's it. Thank you very much.
Thank you so much for your great talk. Now we open the floor for questions. Do we have any questions for the speaker from the audience?
I have a question, and then somebody else will ask questions.
I think Raj.
Raj? Okay, right, go right here, Raj.
Yeah. Hi, Jorge. Very nice presentation. Can you go back to slide 17?
I don't. 17, okay.
Yeah.
Okay.
Yeah, here the second term, why would you drop it like the second term? Because this is some sort of a sense of direction, right?
Yeah,
Only
but you are closer. Well, you can check it. You can check it. We can check it this numerically, but near the minimum, as the gradient is practically zero, you get that. Well, you can check it by the way, and that the term of the Hessian dominates the other one. So if you are closer to the minimum, this approximation, we have checked that it is pretty good, by the way.
Yeah, it's correct because gradient of J is zero. Close. If you're close to a minimum, any minimum, the gradient of J is zero. That's why.
And that's why, like, you have to start first with some EDAM optimizer, then only will be close to minimum, right? You cannot run this optimizer right away, right? You need some sort of warm up.
Can you repeat the question, please?
Yeah. So for this to implement, so you need some sort of warm up, right, before you apply this optimizer, so it gets close to the minimum, right? You cannot apply directly right away.
Yes, exactly. That's it.
But I think, Jorge, I think this is just a motivation to show that with what type of G functions you would work, right?
Yes, exactly. So it's a type of, it's a motivation of how we can to increase the curvature near the minimum, okay, in order to increase the the convergence rate of VFGS. Okay, so this is kind of a justification of why this function could be interesting to try.
Okay. Thank you. Thanks.
These are Jorge. These are remarkable results. These are amazing results, actually. I have a couple of questions. One is, did you combine the two? Did you combine the definition of the loss?
I combine the two. I combine the two, but I get very similar results if I use only, for example, the coefficient, the modifications of the VFGS formula with the standard mean square error loss. And then if I introduce these modifications of the loss function, I get very similar results.
So no improvements if you combine them?
No, no, doesn't seem.
Okay, you didn't show us the secret sauce about TK, tau K, and phi K. Can you show us what did you do for the sequence of tau K?
Okay, so the specific choices of these coefficients.
Yeah.
Okay. Well, this I think is pretty technical, but I need to move to the paper that I have written. So maybe, can you see the screen? And
Yes.
okay, so wait a moment. Wait a moment, because I cannot. Okay, wait. I will go to overleaf in order to. Okay. Okay, it's loading the file. Okay, so the
While
file I
you're,
have.
while you're looking, it seems that you get a comparable accuracy with either way, right? So what it seems then is it the cost? How did you say? Why would you change the phi k and tau k instead of just doing a geo, choosing
Well,
to be a j? Yeah.
no, I present both results.
No, I know, but in routine computation, let's say you advise me what to do now in my project. Should I just
Okay.
use the j instead of
I will use I think what well, I provide you here the expressions for the tau k and phi k parameters, which I think here, which are not complicated expressions at all. So okay,
can I see them? Just can you
wait a moment, because maybe, yeah, okay. So tau k the tau k parameter, one of the combinations that we have tried is this guy. Is this guy, okay? So the yk is the difference of the gradients, and the s sub k is the difference between two iterates, okay? And one important detail here is that it appears the inverse of the hk parameter. And you don't want to invert the matrix because this is very slow. So,
right.
We have put here an appendix in order to, which is here, that this term, which is the inverse of the HK matrix, multiplied by the S vector here, which is the difference between traits. If you use the formula of the line search method,
Yeah, I know that formula. I know that, Jorge. I teach that in my class too. I know that. Yeah. But you in the formulas you have 4 parameters, what you call auxiliary parameters.
Yes. Yeah. These are they're here. Okay, I will move to them.
So that's your secret.
These are the parameters of the self-scale Broyden formula, okay, which are these are these parameters. The parameters here.
So you actually give them. Okay, so these are. So
yes.
Everything is deterministic after you program it. Everything is. It's
yes.
not like the user doesn't have to make any choices then.
No. Because the only thing that you need to introduce are the choices of, I think is tau k, I don't know, and the theta k, which I don't know if this thing. Okay, these choices are the things that change, but then you can compute all the auxiliary variables with these choices. But they are pretty easy to compute, by the way. Not very complicated.
So overall, because you mentioned LBFGS versus BFGS, the cost is different. With the BFGS, you always beat LBFGS, right? With these enhancements, in terms of time, in terms of work clock.
In terms of work clock, well, I have this plot. I also plotted it against I think this is done with for one particular problem. I think it's for the non-linear Schrodinger equation. I think you know the equation. And
I know the
yes,
equation.
what we have done is to compute for example, we compare, for example, the low memory BFGS, okay?
Yeah, nice.
And the low memory BFGS is much faster, okay, than the BFGS for a same game network. So you can perform, for example, here are 40,000 iterations with in the same training time that BFGS with the same network performs 10,000. Okay, so there's a factor 4 of difference. Okay, but as I said, the low memory BFGS has the problem that struggles even more for ill-conditioned problems. So because of that, when you try to increase the number of parameters of the low memory BFGS, you don't get much. You get some progress, but with the BFGS formula, you can obtain with much less variables comparative or even better results. So at the end, you end up, if you compare now the training time, by reducing the number of parameters with BFGS, you can obtain similar results with the low memory BFGS in the same training time, because for the low memory BFGS, you need a lot of parameters.
Right, right.
Yeah.
And my last question is, have you looked at the new Google optimizer called Lion, Lion?
No, no, I
Okay.
haven't.
Because that is something that was discovered by a genetic algorithm, kind of modification of Adam. It seems to, at least that's what they claim.
Lion optimizer. I think I have heard about it.
Lion optimizer from Google, yeah. So that seems to work well, actually.
Okay. I will check it out because, okay. I will check it out. It's like an Adam, okay? Or
it is a variant of Adam. It changes a few lines.
So it's a gradient descent based method. No?
Automatically, but also discovered automatically. It was not like an invention of a person. It was automatically.
Okay. No, I didn't know that. So yeah, I will check it also, because nowadays we are experiencing a boom in machine learning. So there are a lot of algorithms and lots of things that people try. So it's difficult to keep in touch. But yeah, I will check it out.
I would definitely want to. So your code is the code that you have is open source. It's on the GitHub.
Okay. Well, it's in order to modify the BFGS formula, for example, the thing that I have made is I use the SciPy optimizer, and the only thing that I have done is to add some lines of code in order to calculate these parameters, and that's it. So if you want to,
but you don't have your code. You don't have your code on GitHub.
No, not yet, but I will provide them.
Because we'll be interested to compare with some of the examples, especially for high range number flows, where we get this ill-conditioned problem that you mentioned. All multi-scale problems will suffer from that. So
okay. No, my idea is to upload the code that I have used on GitHub. But the thing that I have made is basically to modify the script of the optimized version of SciPy, and I add these coefficients, and then I compute the HK matrices as it is in the SciPy code. So the program is the same, but you add some lines of code, but the greater part of the code is just written, okay? Because the computation of the learning rate and things like that is the same as they use in the SciPy code.
okay, thank you very much. Gracias.
De nada. You're welcome.
Thank you so much for your great talk. So, do we have any other questions?
Okay, wait a moment.
I think, yeah, it's time to move on to the second talk. Thank you so much for joining us today.
Okay.
Yeah, thank you. Shujian, are you there? Thank you. Shujian.
Yes.
Oh, thank you so much. Can you share your screen?
Let me share the. Yeah, can you see my screen now?
Yes. Can you put it on presentation mode?
Okay.
Yes. Thank you. So our second speaker is Shujian Yu. The title of his talk is From Optimization to Generalization, Analysis for Deep Information Bottleneck. Shujian Yu is currently an assistant professor in the Department of Computer Science at the Vrije Universiteit, Amsterdam. He also holds a guest position in the machine learning group at the UiT, the Arctic University of Norway. He earned his PhD in electrical and computer engineering with a minor in statistics from the University of Florida in 2019. Shujian is the recipient of the 2020 International Neural Network Society Ahovan Katsir Young Investigator Award and was selected for the 2023 Triple AI New Faculty Highlights. With that short introduction, the floor is yours and you can start your presentation.
Okay, thanks for the introduction. Hello, everyone. The title of my presentation today is From Optimization to Generalization Analysis for Deep Information Bottleneck. So my presentation contains 3 parts. In the first, I will briefly introduce the basic concepts behind information bottleneck. Then I will discuss separately how to optimize the deep information bottleneck and how to provide some analysis on the generalization error. So the information bottleneck currently has been widely used in representation learning. So first, let us suppose we have input X. We want to learn a good representation T, and usually in machine learning community, there are many ways to define the usefulness of T. For example, we may expect that T is disentanglement, or T is interpretable, maybe in the sense that each dimension of T encodes maybe one physical meaning of the input X. For example, maybe the first dimension of T encodes the color of the X, whereas the second dimension of T encodes the size of the X or something like that. For example, we can consider this example. Suppose the X is our input, it's an image. And suppose now we use a neural network encoder, and the representation we learned from the image is a sentence which says that there is a cat lying on a laptop. Maybe at the beginning, we may feel that this representation T is very, very useful, and because it's a very good summarization of the content in the image. But in machine learning, and especially in information theory community, we may feel that the usefulness of T also depends on the downstream tasks. For example, here, suppose our question or task is that I ask you to determine if there is a cat in the image. So we can obviously see that in the latent representation T, it has 2 kinds of information. The first one is the relevant information because the T contains the information about the cat. So it can be used for us to answer the question, but it also contains some irrelevant information, the laptop, because this such kinds of information does not help us to answer these questions. And now, if I change our downstream task and ask us to determine to answer the question, how many pixels are there in the image? And in this example, we can see that both the information about the cat and the laptop become somewhat irrelevant or cannot help us to do the downstream tasks. So what does it mean? It means that in order to quantify the usefulness of T, the latent representation, it also depends on the downstream task Y. So essentially, we expect that it can be useful for predicting the Y. The Y can be a label or any kinds of any other kinds of information about our tasks. So now in the information theory community, there is a very well-known learning principle to define the usefulness of the T. And usually we need to strike a trade-off between 2 conditions. The first one we call the requirement is about the sufficiency of the representation T. So the physical meaning is that the T is a latent representation of the X, and we know that the mutual information between X and T. X is input, T is the label or the desired response Y. So the mutual information between X and T contains all the information that our input can provide us to make a decision about the Y. And a sufficient statistics means that the eighth X is a summarization of our input X, so it's a latent representation. So the sufficient statistics means that T contains all the information regarding Y that can be obtained from X. So mathematically, it means that at least we expect that the mutual information between the T and Y should be no less than the mutual information between X and Y, because the mutual information between X, Y, and Y is all the information, useful information that X can provide us to predict Y. So the first condition is that we expect the mutual information between T and Y is as large as possible, or at least it cannot be less than the mutual information between X and Y. So this is the first requirement about the sufficient statistics. But there are many sufficient statistics maybe we can extract from our input X. For example, I can require that the simplest sufficient statistics is that I can require that the T equal to X, which means that our neural networks learns an identity mapping. So in this case, we can see that even though the T is a sufficient statistic, it contains all the information that X can be used to predict Y, but we may fear that the T may contain many redundant information, which means, so another requirement to learn a good representation is that among all the sufficient statistics which satisfy the requirement that the mutual information between T and Y is equal to the mutual information between X and Y, we want to just learn the representation such that its complexity is minimum, which means that T only contains relevant information regarding Y, but get rid of any redundant information from the X. So which means that there is some trade-off here. On the one side, we want to maximize the mutual information between T and Y, and on the other hand, other side, we also want to seek or obtain the representation or that is minimum or contains less redundancy about the X, which get rid of any redundancy, something like that. So we also want to minimize the mutual information between T and X. So sum together, put in a one formula. So the bottom is objective for the well-known information bottleneck. We want to maximize the mutual information between T and Y, and also trying to minimize the mutual information between X, T and X. So are there any questions about this formula?
Maybe for the people who don't know this, they don't have background information, you can define what Y is schema for a neural network. I know it's the output, right?
The Y is the label, can be the label, the label, true label, yes.
Yeah, exactly. Yeah.
The X is an input. For example, in the image classification problem, the X is an image. The Y is a label. The T is a hidden layer representation.
That's right. Yeah.
Yes.
Please go on.
Okay. So now, after introduce the basic concept about the information bottleneck, currently it's becoming a popular topic to parameterize the neural networks by leveraging the idea of the information bottleneck. For example, we know that given much layer, as a simple example, a much layer perception, we have the input. We also have the output ground truth, the Y, and we have our estimated Y hat. And the different layers can be understood as different hidden layer representations. We have T1, T2, and T3. And in order to use neural network to parameterize the information bottleneck, then we need to optimize to train a neural network with this loss function, with this objective. Here, theta is a parameter of the neural network. T can be any hidden layer of the neural networks. So the objective is that we want to maximize the mutual information between layer representation and the label, and at the same time, minimize the mutual information between the layer representation and the input. So this is the objective about the deep information bottleneck. Here, X is input, T is a label, Y is a label, T is one of the hidden layer representation. Usually, this is the T3. So, although the objective seems very, very straightforward and easy to understand, we just need to optimize these two terms. But the thing that in information theory, a very, very common problem is that the people always say that estimating the mutual information is usually very, very hard because the X, the T are usually in high or ultra high dimensional space. So which make the precise estimation of the mutual information term is very, very difficult. So the first problem people want to address is how can we optimize neural networks with the information bottleneck objective. Finally, so we can discuss this separately. So the first problem is that how to estimate or optimize the mutual information between T and Y. And it has been proved that instead of directly maximize the mutual information between T and Y is labeled, T is latent representation, people observe that this objective, after some not too hard or straightforward derivation, it somewhat can be approximated or equivalent to minimize the divergence of two functions, two dense functions. The first is a conditional distribution of the Py given X. This is, we know that in machine learning, this is a ground truth mapping from the input X to the Y, but this density function is usually unknown. And the second, it's a probability density function. It's a conditional distribution of the Q theta Y hat given X. Theta is a parameter of our neural network. So this, the second term can be understood as estimation of the Y hat given X and provided by our neural network or any machine learning models with the parameter theta. So so what does it mean? It means that maximize the mutual information between T and Y can be somewhat approximated by just minimize the distance between the two conditional distribution of the Y given X, which is usually unknown with respect to the density conditional distribution of the Q Y hat given X provided by our neural network or early learning machines. So, and also, if, for example, suppose we are dealing with a regression problem and assume that the neural network, the output follow a Gaussian distribution, it can be somewhat, finally, the objective reduces to this one. Sorry, this should be minimized. And we know that this exact, the H theta is our neural networks. And so we can see that this reduces to the well-known mean squared error loss. So the message here is that essentially, at first, we want to maximize the mutual information between T and Y, which is very, very hard. But we can do some approximation by trying to optimize this term. And then if we further assume that the neural network output follow a Gaussian distribution, the Q theta Y hat, and then our final objective is just as simple as to minimize mean squared error loss, which is widely used in almost all the learning machines to learn a regression function. But the thing that we can see that in this process, maybe there are some uncertainty because it's cannot always assume that or guarantee that the output of a neural network always follow a Gaussian distribution. So one question here is that how can we more precisely evaluate the mutual information between T and Y, but without adding parametric assumptions on the output of the neural networks? Another term is that we want to minimize the mutual information between T and X. So this is a mark chain. And so we want to minimize their mutual information. So usually, again, directly estimate the mutual information between T and Y is also sometimes very, very hard because both T and X are in a high dimensional space. So people usually use an alternative way, which means that instead of directly minimize the mutual information between T and Y, people resort to minimize an upper bound on the mutual information between T and Y. And a well-known upper bound is from the rational approximation, and it can be somewhat show that the mutual information between T and Y it's smaller than the K divergence between the distribution of our encoder PT given X with respect to the prior distribution, the VT. And usually the VT is assumed to be a Gaussian. So there are also some other kinds of upper bound based on the rational approximation, or other kinds of approximation has been suggested. So the second question is that, but again, different approximations or upper bound also introduce maybe some error on the computation of the mutual information. So our second question is that how to directly evaluate the mutual information between T and Y, but without using an upper bound or rational approximation. Our motivation is that can be straightforwardly to evaluate the mutual information without using the minimize its upper bound. So together is that the problem is that how can we carry out nonlinear information bottleneck or deep information bottleneck without rational approximations or parametric assumptions such as Gaussian. So originally, as we have discussed, the original information bottleneck in deep neural network community is essentially equivalent to this objective. We want to minimize the Q divergence between the Py given X with respect to the Q theta Y hat given X plus a mutual information regularization term. But both terms require some approximations which are a bit hard to evaluate in practice. And so in order to improve the precision of the estimation and also make the nonlinear information bottleneck can be relatively easy to be optimized, we propose here the Cauchy-Schwarz divergence information bottleneck. And the key idea here is that instead of using the KO divergence, which is usually hard to estimate, or sometimes because KO divergence sometimes also have maybe infinity values, which may hurt the optimization because it may suffer some extreme values. We want to make the optimization more smoothly or more easy to handle. So we resort to replace the KO divergence with the new divergence, which we'll ever introduce later. We call the Cauchy-Schwarz divergence. Here, the first term is that a new way to quantify the distance between the Py given X and the Q theta Y hat given X. And the second term we call the Cauchy-Schwarz divergence mutual information. So just a background knowledge is that the mutual information actually is a way to quantify the dependence between two random variables and X and T. And we know that if the joint distribution between X and T equal to the product of the margin distributions Px and Pt, and we can see that these two random variables are independent to each other. So which means that if we can use a distance measure to quantify the closeness between the joint with respect to the product of the marginals, this quantity can be set as a valid quantity to quantify the degree of the dependence between two random variables. And the classical mutual information is exactly the KO divergence between the joint and the product of the margin distributions. But here, the Q divergence, as we just mentioned, is a bit hard to optimize. So we resort to use a Cauchy-Schwarz divergence, a new way to quantify the distance between the joint and the marginal distribution of these two random variables. So we call this Cauchy-Schwarz divergence induced mutual information. So now maybe I go a bit quickly. Some background of the Cauchy-Schwarz divergence. Currently, in statistical community, there are two ways. Suppose we have distribution P, and we also have another distribution Q. And currently in the machine learning community, there are roughly two ways to measure the difference or closeness of two distributions. One is to the general idea to measure the P, directly measure the P minus Q, and this family of distance is usually called the integral probability matrix. For example, the well-known max-min discrepancy, and the general idea is that suppose we have samples X from distribution P, we also have samples Y from distribution Q, and we want to learn a mapping function phi such that we want to seek the maximum distance between the expectation of the phi X minus the expectation of the phi Y. So this is definition of the MMD, max-min discrepancy. The general idea is to directly evaluate the difference between P minus Q. And another big family of distance, people call this as the F divergence. And the general idea is that instead of use P minus Q, we resort to the idea to quantify the ratio between P over Q, because we know that if the two P equal to 2, then their ratio equal to the 1. So for example, the well-known K divergence is defined as the expectation of the log of the Px over Qx. And so this is definitely and is defined using the ratio of the P over Q. But here, the Cauchy-Schwarz divergence, the general idea is a bit different. So it does not rely on the difference between P minus Q, or it also do not rely on the ratio of the P over Q. It's evaluated by quantifying the tightness of an inequality associated with two density functions. For example, we know that from the Cauchy-Schwarz inequality for Allen square integral functions, suppose P and Q are two density functions, we know that the Cauchy-Schwarz inequality states that the square of the integral of the inner product between P and Q should always be smaller than or equal to the product of the integral of the square of the density functions. And we also know that if and only if the Px equals to the Qx, the inequality becomes the equality. So what does it mean? It means that we can use the tightness between the left side and the right side of this inequality to quantify the closeness between these two for any two functions, P and Q. For example, we can directly use the ratio of the left hand of the right hand over the left hand of this inequality, and then put a log outside. And this way we can define this quantity. We can use this quantity to define the closeness between any two density functions, because the log, the ratio is always larger than 1, and it takes the value of the 1 if and only if the Px equal to the Qx and the log of 1 equal to the 0. So which means that this quantity itself is always larger or equal to the 0, and if and only if Px equal to the equals to the Qx, the log of this ratio equal to the 0. So which means that mathematically, this is a valid way to define the closeness of any two density functions.
So, Jan, can you say why the Cauchy-Schwarz, the way you define it, divergence is easier to evaluate compared to, let's say, the MMD?
Yes.
Or the KL.
Okay.
What makes it easier?
Oh, yes.
The same quantities are involved. Let's say with the KL divergence, yeah.
Okay. So we first discuss maybe the Q divergence, because the thing that essentially the Q divergence is defined over P and Q. So it have maybe a well-known problem is that suppose the Qx it's very, very small or goes to 0. And in this case, the log of the maybe an infinity very, very large value maybe goes to infinity. So which makes if we use a Q-divergence to optimize our objectives, usually the optimization may be very, very unstable because we cannot always guarantee the support between P and Q are overlap. So this is one main issue of the Q-divergence in the optimization. It's sometimes a bit hard to guarantee the overlap of the P and the Q. But the Cauchy-Schwarz divergence does not have this issue, which means that in almost all the cases, the Cauchy-Schwarz divergence is a finite value. It will never goes to infinity.
Because P and Q are not separated.
Yes, exactly. We do not need to require that the P and the Q have the same the support
Right.
are overlap.
Yeah, yeah. All right, thank you.
Okay. So, and the thing
excuse me, I
okay.
want to ask a question here. This is Panos Tinis from Pacific Northwest National Lab. What you say, I don't see why the Cauchy-Schwarz inequality will not give you a problem, because in the denominator you have the integral of px times qx, right?
Yes.
So if px and qx have supports which are, disjoint,
oh, exactly.
then the integral in the denominator will be very small.
Yeah, exactly. So maybe I can use this figure to show more clearly. So the thing that we need to differentiate, if the support between P and Q have no any support, then all the both the K and the C goes to infinity. So this indeed, but the thing that the Cauchy-Schwarz will have finite values, and in even though the maybe the forward or reverse Q-divergence, one of them goes to infinity. But in both cases, the Cauchy-Schwarz divergence still be of
Why is the situation in the middle giving you the DKL going to infinity? The situation in the middle that you have, the one in the middle, you say that for the one in the middle, the Cauchy-Schwarz divergence will be finite, but the other one will be infinite. Why is that?
Because the thing that we need to evaluate the log of the ratio of the P over Q. For example, we see at this point, if we use a reverse of the K divergence, the Q, and we need to evaluate the log of the ratio of the Q.
I see that one. Okay, all right. But the other one will still have, the Cauchy-Schwarz will still have some overlap, so you will get something that is non-zero.
Yes, if the P and Q only have a small overlap, the Cauchy-Schwarz
you still get something. But when you say finite, it can still be small, right?
Yeah.
Sorry, it can still be large.
Maybe it still be large, but
the denominator does not have to be zero, but okay. All right. Yeah, thank you.
No. And then the thing that another way is that Cauchy-Schwarz divergence itself also closely related to the max-min discrepancy. So it's not too hard to derive some sample estimator on the Cauchy-Schwarz divergence. Here is that suppose we have m samples drawn from distribution P. We also at the same time we have n samples drawn from distribution Q, and we can use a kernel-based estimator to derive both the sample estimator to the Cauchy-Schwarz divergence and the max-min, the MMD. And very, very interesting, we found that they are very, very related, closely related to each other, because both estimators depends on 3 kernel metrics. So the basic logic is that both divergence can be interpreted as we need to first evaluate the within distribution similarity and in 2 distributions, and -2 of the cross distribution similarity. But the similarity is evaluated with a kernel function. So this, and maybe this is maybe go a bit deeper. But the thing that maybe I use this figure is more easy to illustrate. So the MMD, the general idea is that we want to learn a mapping function and phi x, such that we want to maximize the expectation of the phi x minus the phi y, and suppose that the empirical, suppose we have m samples from the P, and the mu P is set as the empirical kernel mean embedding, and the mu Q is set as the empirical kernel mean embedding for the samples in distribution Q. And it can be shown that the MMD essentially is just to quantify the Euclidean distance between the two kernel mean embeddings mu P minus mu Q. Whereas the Cauchy-Schwarz divergence, instead of measure their Euclidean distance, it measures the cosine similarity between the mu P and the mu Q. So this is the first relationship between the estimator of the Cauchy-Schwarz divergence with respect to the estimator of the maximum discrepancy. So which means that even though the Cauchy-Schwarz divergence itself is not defined with integral probability matrix or defined user ratio of F divergence, but at least the estimator, it still has closely related to the MMD. One quantifies the Euclidean distance, but the Cauchy-Schwarz divergence quantifies the cosine similarity, which means the theta. And but on another side, the Cauchy-Schwarz divergence is also closely related to the K divergence. This relationship is can be reflected from another inequality, and which we call the Holder inequality in statistics. And the Holder inequality in statistics states that for a lambda larger or equal to the 1, there is an inequality associated with two density functions P and Q. The inequality states like that. And it can be shown that if we take the value of lambda equal to the 2, then we can obtain the Cauchy-Schwarz divergence. But on the other hand, if we use the value of the lambda very, very close to the 1 or even equal to the 1, then we can obtain the K divergence. So this it means that both the Cauchy-Schwarz divergence and the K divergence can be seen as a special case of the generalized Holder divergence. But one is just use the value of take the value of lambda equal to the 2. Another is to take the value lambda equal to the 1. So yes, so this is some background of the Cauchy-Schwarz divergence, and also we show that its estimator is closely related to the maximum discrepancy and relatively easy to evaluate from samples compared with the K divergence. It can also avoid, for example, the instability of the training. So those observations motivate us to replace the K divergence in the original deep information bottleneck objective, and then both quantity we want to evaluate cannot use a Cauchy-Schwarz divergence. And we show in the paper, again, we need to estimate two terms. The first one is a conditional phase divergence between the Py given X with respect to the Q theta y hat given X. The second is mutual information, the Cauchy-Schwarz divergence between the joint and the product of the margin distributions. And for the first term, the Cauchy-Schwarz divergence between Py given X and the Q theta y hat given X. And we show it can have a closed form or sample estimator expressed in this way. And similarly, and for the second term, on the mutual information between X and T, usually people say this may be a bit hard to evaluate, but in our paper, we show that even for the mutual information between X and T, defined with the formula of the Cauchy-Schwarz divergence, it can also have a final elegant sample estimator expressed in this way. So the key message is that for both terms, we do not need to assume, for example, Q theta y hat follow Gaussian. We also do not need to use maybe a versional approximation, but directly evaluate both terms straightforwardly without adding approximation or Gaussian assumptions. So sum together, we combine, so we call this objective as a Cauchy-Schwarz divergence information bottleneck. And we indeed do some comparisons with other ways to optimize information bottleneck. So currently in the community, there are many ways to optimize this objective, how to maximize mutual information between T and Y, and also to minimize the mutual information between T and X, and there are many ways. And our ways to leverage the Cauchy-Swan divergence and without any versional approximations. And we indeed compare with other ways that relies on some different kinds of approximation strategies. And we observed that our method can always maybe find the best trade-off between prediction and the compression. So here, let me explain. The x-axis is a compression ratio, and the y-axis is mutual information, the ground truth mutual information between T and Y. So which means that how many information we can obtain about the ground truth label Y can be obtained from our latent representation T. So X, it's a compression ratio, which means that how many, it measures how many redundant information about X are dropped out by our information bottleneck objective. We can see that if there is no compressions, which means that we do not get rid of any redundant information, all the method can achieve a good prediction performance because it makes sense because without any compression. And on the other hand, if we give the maximum compression, which means that maybe guarantee that the T is completely independent to X, so T learns nothing from the X, so compress all the thing about the X, we can expect that the prediction performance of the T is also very bad. But the interesting is that maybe we can see the alpha approximated to the, here in this example, 0.3, it means that the T get rid maybe 30% of the redundant information in the X, but it can further may even achieve maybe better or no slightly better prediction performance than the without compared to without adding compression. So this is so which means that by introducing some slight compressions, the prediction performance for most information bottleneck can improve. So this phenomenon holds for different data site. And
what are the units of I here? Or
this is
bytes?
The mutual information. We use ground truth evaluated with Monte Carlo simulation.
No, the units of I.
Bits. Yes.
Bits, yeah. Looks very low.
Yeah, and maybe it depends on the data, and I think
usually it's of the order of tens or something like that.
Yeah, maybe it depends on the data.
Okay.
And but the most interesting is that we and also maybe one of the key message, the logic behind the information bottleneck is that currently the community says that in order to improve the generalization performance, the compression term is very important. So which means that many people say that it's just because by introducing the regularization term to trying to minimize the mutual information values between T and X, it can improve the generalization behavior of neural network. And this objective, the kind of information bottleneck objective, has been widely used in different computer vision or natural language processing or even deep learning or reinforcement learning experiments. And many people heuristically say that by trying to minimize this term or regularize this term, it can improve the generalization performance. So this is indeed, we also validated this observation and here this figure is that we train 100 independent neural networks and guarantee that each neural net are independent trained, and each neural network are with different maybe the size, different depths, or different weights, or different maybe activation functions. But each neural network can obtain a reliable performance on our data. And so there are 100 individually trained neural networks. And in each neural networks, we evaluate two values. The first one, the y-axis, it's an empirical generalization gap, which means that the difference between the training loss and the test loss. The y-axis its degree of compression. So the y-axis is either the mutual information between the x and t, or the conditional mutual information between x and t given y. And we indeed observe that in this maybe a relatively simple data set, we roughly observe maybe a positive trend between the degree of compression with respect to the generalization gap. So which meant maybe the more compression on the mutual information term between x and t, the smaller the generalization gap. So then this phenomena is currently maybe in the community that people want to have some justification if or not the compression indeed imply the generalization. But this figure is just empirical results. But indeed, so now we move to the last part. We want to have some theoretical analysis to justify if compression imply good generalization performance. So I will quickly go through this term. So in statistical machine learning, and we have our training set, n samples. Zi is a combination of the input and the label xi and yi. We have n samples drawn from a training distribution, unknown distribution mu. And we also want to learn a hypothesis, maybe in a hypothesis space. And suppose there are d number of parameters inside the neural networks, then the hypothesis space of neural networks is just a subset in a d-dimensional space. And we also have our loss functions. So in the regression case, usually the loss function is just the square of the difference between y minus fwx. And any learning algorithm can be understood maybe as a mapping function from the training set to map to a hypothesis space. And in this case, and we have our training loss, so which is that it can be understood as the average of the loss for each of the samples in the training set. So this is our training loss, and at the same time, we also have the population test loss, or which is also called the population risk. So which means the loss, the hypothesis evaluated on the z such that the z is drawn from the unknown distribution mu, and the generalization error usually mathematically it's the absolute difference between the test loss and the training loss. Now, indeed, currently, after maybe several years of development, people in the last year, Dr. Kawaguchi in an ICML paper maybe give maybe the first rigorous bound on the information bottleneck about the generalization, which to the key message is that the generalization can indeed be improved by compressed reputations. The informal statement is that for some fixed W, the hypothesis, maybe the learned parameters, and with probability 1 minus delta over the training samples S, the generalization error can be upbounded by the conditional mutual information between x and t given y, and we can see that this is exactly the compression term inside the information bottleneck. Originally, the information bottleneck, the compression term, is compressed as a mutual information between x and t, but it can also be expressed as a conditional term between x and t given y. So the thing that maybe the theoretical result in the last year maybe is one of the first rigorous proof to show why information bottleneck regularization can improve the generalization performance of deeper neural networks.
Why the THP result is not? Is it because it's the exponent?
Yeah, it's Yes, its exponent is not that tight, and it's hard to quantify the loss of this tightness of this bound, the two of the exponential. So compare these two, it becomes much tighter.
Okay.
And but the thing that this bound is very interesting. It shows one key message that indeed maybe some kinds of compression can indeed induce or imply generalization. But the thing that even this bound is very interesting. But sometimes maybe we may also feel that it a bit still gives some difficulty to justify the tightness of the bound, because again, the mutual information between X and T is somewhat very hard to compute or evaluate. And also in some cases, the mutual information between X and T can also goes to infinity. And so because of these limitations, and we trying to think a way if it's possible to further tighten the bound provided by Dr. Kawaguchi. So because of the limited time, I just show the motivation. Is that here, the first figure shows the flow of information inside the deep neural network. We have the input, the Y, the label, the ground truth label determines, usually people say determines the input, the X. And inside the neural networks, it follow Markov chain, the X to the first layer, to the second layer, to the Lth layer, and the L is loss. The L2 norm or the cross interval loss. The L is the loss function, it's a final loss. And the L can be maybe a squared error loss or cross interval loss. And because we see that the computation of the loss also depends on the true value of the ground truth value Y. So it means that there is another flow of information directly from the Y to the L. So given this information flow inside the deep neural networks, and we have the conditional data processing inequality, which states that the conditional mutual information between X and T1 given Y, it's always larger than or equal to the conditional mutual information between X and T2 given Y, and larger or equal to the conditional mutual information between XTL given Y, and finally it's larger or equal to the mutual information between XL given Y. And some other motivation is that if the neural network is deterministic, and then it can be shown that the entropy of the loss given XY equal to the 0. So sum together, it means that we have maybe that there is quantity. This is a conditional entropy of the loss given Y. This quantity should always be smaller than the conditional mutual information between X and T given Y. So because of this relationship, and so this quantity, the conditional entropy of loss given Y is always smaller than conditional mutual information of XT given Y. So our motivation is that if can we use the conditional entropy of the loss given Y to further tighten the bound provided by Dr. Kawaguchi in the ICML. And very luckily, and we indeed with some mathematical proofs, and we provided another bound. And which means that we can justify that the generalization error of neural networks is indeed can be upper bounded by a quantity, but currently instead of the associated with the mutual information between XT or mutual information between XT given Y, now the new bound is that it can be upper bounded by the conditional entropy of the loss given the Y. But we need to be aware that because of this bound, we can significantly simplify the evaluation of the tightness of the bound, because we know that the conditional entropy of the loss or the entropy of the loss is very easy to compute, because the loss function, the L, is just one-dimensional. Because suppose we just evaluate the mean squared error loss, the L just equal to the Y minus FW X. So this is just a one-dimensional random variable. So evaluate the entropy of the one-dimensional random variable is very, very easy compared to evaluate the mutual information between X and T. So indeed, in the same synthetic data, same to the ICM paper in the last year, and we train 216 different models in total, and we indeed observe that positive correlation between the impractical generalization gap with respect to the either entropy of the loss or the conditional entropy for the loss given the y. So which meant the empirical result, these empirical results justify the correctness of our theoretical results. And also we also compared with the results from the ICM paper in the last year, and we can see that by the entropy or conditional entropy of the loss is indeed a better evaluator or indicator to quantify the good generalization performance of neural networks. And so this, which meant awesome. So now the summarization is that conclusion is that we introduce the basic idea behind the information bottleneck, which can be understood as an approximation to the minimum sufficient statistics. And usually in deep neural networks, people optimize the information bottleneck trying to rely on K divergence to evaluate both terms. But we show that by replace the K divergence with the Cauchy-Schwarz divergence, the estimation and the optimization can be much, much more stable. And also theoretically, we also, and with the efforts from in recent years, there are also some theoretical results to justify why compression, especially the term on the mutual information between X and T, can improve the generalization performance. And originally, there is a bound expressed in this way, which can be further bound, make it tighter in this way. But the key message is the same, is that compression may indeed can imply the good generalization performance, but how to achieve the compression or compress which term depends on applications. But the key message is that compression is good. And maybe also we do not need to use mutual information or entropy to evaluate the degree of compression. There are also other ways, flexible ways to measure the compression. But the thing that the key message is that maybe some kinds of compression can indeed improve the generalization performance of deep neural networks. Thanks.
Thank you so much for your great talk, Shujian. Now we open the floor for questions. Do we have any questions for the speaker?
Yeah, I have a question, Shujian.
Yes.
First of all, that's excellent because it's very clear. I told you I teach this information bottleneck theory in my class. Also, recently we have our own information bottleneck theory for pins, which includes one who's in the picture there is one of the co-authors of the paper, but includes 3 stages from fitting to diffusion to total diffusion. So we identify a 3rd stage.
Oh.
But my question to you is, you didn't talk about at all about this phase transition in the basic theory of
yes.
HP. You have this phase transition, and the question is, can you use the Cauchy divergence, Cauchy-Schwarz divergence, to pinpoint the phase transition? At what time? At what type? And then by analogy, we could do that for pins, or I think all the other neural networks, there are actually 2 transitions, not just 1 transition.
Yes.
Yeah.
Yes, it's very good. I remember before, because when I was a PhD, we indeed trying to plot the transition phase of a neural network at that time, because in the first paper from Dr. Tishby, he sees that the training of the dynamics have two phases. The first is fitting, the second is the compression. I remember there is a figure which is called the information plane.
Information plane. T is
yes,
called T information plane. Yeah.
And in the information plane, the x-axis is mutual information between x and t. The y-axis is a mutual information between
T
and y. And usually, the curve in the information plane looks like this. So which meant from the beginning of the training, both mutual information values are very, very small. But as the training moves on, the mutual information values increase. But
there's the inflection point, and there's the inflection point there where you point. Yes, exactly.
Yes, we did not use Cauchy-Schwarz divergence to quantify this term, but we use some other estimators. We observe that maybe this figure generally holds for even including the convolutional neural network or some other neural network, but at that time, our conclusion is that in order to observe, we always feel that the compression phase always exists. But in order to observe the compression phase, it depends on the quality of the estimator, because not all the quality of estimator are different, and because it's a common problem to how to precisely estimate the mutual information between xt and the mutual information between t and y. And we found that with a good or reliable mutual information estimator, the increase and decrease phase always exist. And it's also holds for different architectures and activation functions. And we expect that if we use Cauchy-Schwarz divergence, and we can also observe the similar phenomena, but we did not do experiment. But it would be...
Yeah, as I said, this is the old picture. Actually, the compression, that's what our work shows, that the compression stage is actually two stages. It's the early diffusion and the late diffusion.
Okay.
And we have, and the way I think Tishby also introduced that, but we use the signal to noise ratio, and that signal for the gradients, and that gives you a universal scenario from fitting to compression, but the compression, as I said, has two stages. That's important. That's a new finding. And the question is, could we use Cauchy-Schwarz divergence to actually pinpoint those two transitions? Not just one transition.
We did not try, but it's a very, very good suggestion. Could you please share me the paper that you just mentioned?
Yeah, I think Juan can put it on the chat.
Sure, okay. I'll put it right now. Here, I put it in the chat.
Okay. Thanks for sharing. I will take a read after.
Maybe if you open it, I can show you one figure that actually summarizes what we're saying, because it's
okay. I will open.
Juan, the sketch, is it in the archive? Is it figure 1, right? Or you updated the archive?
No, in the archive is figure 1, yes. Figure 2. Figure 2.
Figure 2. Yeah, if you go to figure 2.
Figure 2.
Yeah, there.
Yeah, right here. Yeah. This is what I was talking about. You can see and this our tests show, and there's some theory there, that this is actually universal. It doesn't matter it's pins or neural or regression and so on. But you can see that the transition from the first dotted line, vertical dotted line, has there's two transitions. One where the SNR is the signal to noise ratio is below 1, and one that goes above 1. And it's a deterministic versus stochastic regime. So this is very important. So it would be nice, actually, if we can work together to identify through the Cauchy divergence this transition.
It's very interesting.
Because we have lots of examples later. You can take a look at the paper where you actually pinpoint that. So it's a more refined theory compared to Tishby.
Thanks for sharing. The paper is very interesting.
And also, it's one number, the SNR, right? One quantity that determines all that. Yeah.
Thanks for sharing. I will take a careful reading in the weekend. Thank you.
Yeah. Yeah, but anyway, excellent talk because you gave a lot of background for people to appreciate information bottleneck theory.
Thank you.
I saw your work. I thought it was terrific. That because what hinder progress is exactly the inability to compute this mutual information.
Yes.
As you point out, for deterministic systems, is really the so we are. If you look at our paper, we also have that.
Okay.
We replace the mutual divergence with entropy. L
Oh,
over
it makes
because
sense.
we use that in the. But so this is very it's excellent work. Thank you very much for.
Thanks for sharing the paper.
Yeah, thank you so much. Do we have any other questions?
Juan, do you have any questions?
Yeah, maybe. One of the questions that I had is like in your slides, if you go to one of the things that you were mentioning is like about that when you compute the probability, right? You compute the probability between x given y and also the prediction of y given x. You said that one of the issues that we had was like we did not have like a straight way of getting those values. But when you kept talking, it was really nice you introduced my AirPods died. Can you hear me?
Yes.
Yeah, sorry about that. Okay, so but then you talk about like the method about that you propose that is really great about to measure the compression, but how did you compute, for example, the probabilities? Because you said that in the original case, for example, you have to make the assumption that your probability is Gaussian.
Yeah.
But in your case, you don't have to make the assumption.
Yes, we do not need to assume
I got a bit, but then in that part you just went through that part I didn't understand. Why can you in that case, if you're not assuming the probability is Gaussian, how do you make that is additional connection?
Oh yeah, the thing maybe maybe in this case, the thing the things are here, it's a sample estimator, which means that we suppose we have the samples. So maybe in a mini batch we have the input. We also have the ground truth y. We also have the estimator of our neural networks. So this estimator is derived. It's a sample estimator. Suppose we have the samples, but without any assumption on the Gaussian or some others, how to derive a sample estimator based on the Cauchy-Schwarz divergence. So this is sample estimator and evaluated on the x and y and y hat. And in order to derive the sample estimator, we use some kernel trick and in the paper. So a bit similar to the MMD, but so this is a final expression, but it's a bit complex than the mean squared error loss. But we show maybe it's why it maybe sometimes outperform the mean squared error loss. But this is a final sample estimator.
Oh, okay, got it. Yeah, okay, great, thank you. Also, another question was like, when you were like mentioning the compression, did you observe some type of difference between the amount of compression between, I don't know, like the outer layers and the middle layers and the layers that are?
Oh, it's indeed it's before when we use, maybe it's not Cauchy-Schwarz symmetry information, but some other estimators, because before in our lab, we also use maybe we call the matrix-based entropy function also, which is that use eigenvalue of a symmetrical positive definite metric to define the mutual information or the entropy. And with that estimator, we indeed observe that the compression and the fitting and the compression phase may be a bit different in different layers. Maybe some layers maybe first show the compression trend, but maybe some layers the compression trend is a bit later. And I remember, but the thing that maybe most of the layers can have the compression, but maybe first layer first have the compression followed by the second layer. So
and we have the last figure that we have, one of the last figures we have in the paper talks about the binarization of the compression. So you will see also there we discriminate which ones. It's kind of new finding also there.
Okay, thank you.
Not really.
Yeah, actually, I was asking for that because in our case we observed something quite interesting, and it was like we had like more compression in the middle layers,
Oh,
but
In the
not
middle.
so much compression in like all the edge layers.
oh,
So that was
very,
asking if you observed something similar.
yeah,
But
very interesting. Thank you.
okay, yeah, but it was a really nice talk, and it was like, thank you so much. It was really, thank you so much because you went into all the details. So thank you for that.
Thank you.
Thank you so much. Do we have any other questions? I don't think so. So it's time to close the session. Thank you, Shujian, for joining us today. Thank you, everybody.
Thanks for the invitation.
Yeah. I hope everybody have a great weekend ahead.
You too.
Yeah. Thank you.
Thank you.
Bye.